Kirchhoff's laws. We have seen we can analyze simple circuits using Ohm's law and the rules for series and parallel combinations of resistors. There are, however, many ways in which resistors can be connected so that the circuits formed cannot be reduced to a single equivalent resistor. Then we cannot simply use Ohm's law alone to find the voltage or currents circulating within the circuit. For these types of circuits, we need certain rules which allow us to obtain the circuit equations, and for this we can use Kirchhoff's laws. Thanks for watching this video, and don't forget to like, subscribe to the channel and activate the notifications. It's very important to the continuity of this channel. When analyzing circuits using Kirchhoff's laws, a number of definitions and terminologies are used to describe the parts of the circuit being analyzed, such as nodes, branches, and loops. These terms are used frequently in circuit analysis, so it is important to understand them. So we now will see common circuit theory terms. Node. A node is a junction or connection within a circuit where two or more circuit elements are connected. A node is indicated by a dot. Branch. A branch is an element or group of components such as resistors and source which are connected between two nodes. Loop. A loop is any closed path going through circuit elements. To draw a loop, select any node as a starting point and draw a path through elements and nodes until the path comes back to the node where you started. There is only one rule. A loop can pass through a node only one time. Pay attention. We now are familiar with the definitions of node, branch, and loop. Then, let's see the Kirchhoff's laws. Kirchhoff's first law. At any node junction in an electrical circuit, the sum of currents flowing into that node is equal to the sum of currents flowing out of that node. Whatever current enters a given point in a circuit must leave that point because charge cannot build up or disappear at a point. This rule is often called Kirchhoff's junction rule or Kirchhoff's current law. It's simply a statement of the conservation of charge. Kirchhoff's second law. The sum of voltage rise equal the sum of voltage drops around the loop, or the sum of the electromotive forces around the loop is equal to the sum of the potential drops around the loop. This law is simply a statement of the principle of conservation of energy. Conventions for Kirchhoff's second law. The following conventions apply for determining the sign of potential difference across circuit elements. The travel direction is the direction that we choose to proceed around the loop. Draw a loop through the circuit and put an arrow on it, red loop. This indicates the direction in which we will go around the circuit. In the left-hand diagram, we have chosen a clockwise direction. The loop takes us through the cell from the negative to the positive terminal, and so we count the voltage as positive voltage. In the right-hand diagram, we have chosen a clockwise direction. The loop takes us through the cell from the positive to the negative terminal, and so we count the voltage as negative voltage. Next, we go through a resistor. If the loop direction is the same as the direction of the current, so we take the voltage across the resistor as negative. If the loop direction is in the direction opposite the current, so we take the voltage across the resistor as positive. Let's see how Kirchhoff's laws work, from simple to more complicated circuits. Determine the values of the current flowing through each of the resistors in the following circuits. This is a very simple circuit, and we can find the electric current quite easily using the Ohm's law. But we will find the current using the Kirchhoff's second law. This new approach is best used for complicated circuits, but once you master it, you can easily apply it in simple circuits as well. First of all, we need to choose the direction of the loop. In this problem, let us choose the clockwise direction. The direction of the current is given. Now follow the loop starting anywhere. We will choose to start at point S. As we travel along the circuit, we calculate the sum of the voltage across each resistor or cell that the loop takes us through, according to the conventions above. Follow the clockwise loop. First, we go through the cell whose electromotive force is 12 volts. The loop takes us through the cell from the negative to the positive terminal, and following the conventions, the voltage is positive. Next, we go through a resistor. The loop direction is the same as the direction of the current. So, following the conventions, the voltage is negative. We now apply Kirchhoff's second law. The sum of the electromotive forces around the loop is equal to the sum of the potential drops around the loop. Or, in other words, the sum of the potential differences across all the elements around any closed circuit loop must be zero. This equation allows us to solve for the current as 0.5 amperes. Consider now the circuit with two cells shown in figure. We now choose a loop along which to travel through the circuit. We choose an anticlockwise loop. Draw the arrow for the current. With two cells, it is not obvious what the correct direction for the current is, but it does not matter, as we will see. We go through the upper cell from positive to negative, so following the conventions, the voltage is negative. We go through the lower cell from negative to positive, so following the conventions, the voltage is positive. Next, we go through the resistors. The loop direction is in the direction opposite the current. So we take the voltage across the resistors as positive. We now apply Kirchhoff's second law. The sum of the potential difference across all the elements around any closed circuit loop must be zero. The cells give minus 12 plus 9, and the resistors give plus 4 times current and plus 6 times the current. So with this equation for the current gives 0.3 amperes. The current has come out with a positive sign, so our original guess about its direction is correct. Had the current come out negative, the actual direction would be opposite to what we assumed. Consider now the circuit with two cells and four resistors as shown in figure. First, we assign directions for the currents. Again, it does not matter which directions we choose. We have two loops. For the bottom loop, we choose the direction of clockwise rotation. For the top loop, we choose the direction of anticlockwise rotation. We go through the top cell from negative to positive. So, following the conventions, the voltage is positive. Next, we go through the resistors. In the top loop, the loop direction is the same as the direction of the current in each resistor. So, following the conventions, for all resistors, the voltage is negative. We now apply Kirchhoff's second law. We go through the bottom cell from negative to positive, so following the conventions, the voltage is positive as well. Next, we go through the resistors. In the bottom loop, the loop direction is the same as the direction of the current in each resistor. So, following the conventions, for all resistors, the voltage is negative. We now apply Kirchhoff's second law. Unfortunately, we get two equations for three unknown currents. So we need a third equation to solve the system, and the third equation comes from the Kirchhoff's first law. This law states that at any node in an electrical circuit, the sum of currents flowing into that node is equal to the sum of currents flowing out of that node. We can express this law mathematically at node J as follows. We can solve this equation for the current I sub 1. So the top loop equation becomes we now join together the bottom loop equation and the top loop equation to get a system of two equations in two unknowns. We can solve either by hand or with technology. The positive answer we obtained for the current 3 means that our choice of direction for that current is correct. However, the negative answer for the current 2 and current 1 indicate that our choices for those currents are wrong. Nonetheless, the magnitudes are correct. Thus, as a last step here, we correct the answers by reversing the arrows for those currents and then rewrite the answers. Choosing the right directions of the currents at the outset is unimportant because the equations are linear, and wrong choices result only in a minus sign in the answer. This shows us that the initial choices are indeed arbitrary. Consider now the circuit with 2 cells and 3 resistors as shown in figure. First, we assign directions to the currents. Again, it does not matter which directions we choose. We have 2 loops. For the left-hand loop, we choose the direction of anticlockwise rotation. For the right-hand loop, we choose the direction of clockwise rotation. When you have a circuit with more than one loop, start applying the Kirchhoff first law to some node. This will simplify the next equations because it reduces the number of currents that need to be found. We apply the Kirchhoff's first law at point C by writing Let's start looking at the left-hand loop. We traverse the loop in the anticlockwise direction. Applying Kirchhoff's second law, we obtain the equation. Look at the right-hand loop. We traverse the loop in the clockwise direction. Applying Kirchhoff's second law, we obtain the equation. We now replace the current 3 with current 1 plus current 2. We get 2 equations for 2 unknown currents. Solving the system, we find the currents. As a last step here, we correct the answers by reversing the arrows for those negative currents, and then rewrite the answers.